Hello and welcome to Unit 7, Lecture C. We're going to talk about covalent bonds and a couple of special types of covalent bonds plus metallic bonds today. So we talked about ionic bonds last time, and in ionic bonds the electrons are actually transferred. So in this example of making calcium chloride, the calcium has 2 valence electrons. The chlorines each have 7, so they each have 1 open spot in their last orbital. 1 electron from the calcium goes to one of the chlorines, 1 goes to the other. Calcium has a +2 charge, each chlorine has a -1 charge. All the electrons are accounted for, the opposite charges hold them together. That's an ionic bond. So this one is ionic. Today we're going to talk about covalent bonds. If the difference in electronegativities is not great enough to actually remove the electron from the orbital that it's in, instead of making ions, their orbitals will just overlap and they will share the electron. So this right here, this overlapping and sharing of electrons is your bond. That's a covalent bond. So here, using Bohr models, each hydrogen has 1 electron in its valence orbital, remembering that each orbital can hold 2. The orbitals line up and they overlap and share those electrons. So this is a covalent bond. Covalent bonds are all about the sharing of electrons. Generally it's 2 nonmetals. Their orbitals overlap. This is, they're calling it a silicon atom. Carbon will do the same thing because carbon also has 4 valence electrons, and those electrons overlap, forming covalent bonds. If we have 2 elements that are exactly the same, they have the same or very close electronegativities, they are going to share their electrons equally. So what that means is the nuclei are pulling on the electrons with the same amount of force. So this nucleus is pulling those electrons, the pair, the same amount that this nucleus is pulling on this pair of electrons. And so they have to share the electrons equally. They will spend an equal amount of time orbiting this nucleus as they do orbiting the other nucleus. That's called a nonpolar covalent bond. They're shared equally. Generally, this is between 2 elements of the same, or 2 atoms of the same element. Usually the same element. So in all of our diatomic molecules, or if we make chains of carbon, and you have carbon sharing electrons with carbon, if it's 2 of the same element, make a nonpolar covalent bond. Your other choice is to have a polar covalent bond, where the electrons are shared unequally. So if I pair chlorine and hydrogen, the chlorine will pull on the electrons much more than the hydrogen will because it has a higher electronegativity, and it will share it unevenly. The electrons will spend more time with chlorine than they will with the hydrogen. And so the chlorine side will pick up a partial negative charge because sometimes he has extra electrons, and the hydrogen will sometimes have a partial positive charge because he's missing his electrons quite often. So equal sharing, nonpolar; unequal sharing is polar. There's another type of covalent bond that's a special case that we call coordinate covalent bonds. And these are going to be how our polyatomic ions generally form. In a coordinate covalent bond, the electrons are shared, but they're shared 2 of them from the same atom. So if we look at nitrogen, he has 5 valence electrons. This is an unshared pair of electrons because those two electrons are in the same orbital. They're filling the orbital up. The orbital can only hold 2 electrons. These single electrons are called lone electrons. So if we make ammonia, the compound, and we have nitrogen and 3 hydrogens, each hydrogen has 1 valence electron. They share their 1 valence electrons with the lone electrons. And so now I have ammonia, NH3. We have a shared pair of electrons, also called a covalent bond. So shared pair of electrons is also called a covalent bond. We can have this thing called ammonium, the polyatomic ion, which is NH4 plus 1. And you start with just your plain ammonia. And generally you have water, because they have to show me, I want to show you where your hydrogen is coming from. The hydrogen gets ripped off of the water, leaving behind his electron, which now makes this a negative hydroxide ion. And your hydrogen, who has no electrons now, is positive, and he hooks on to this unshared pair of electrons. That is your coordinate covalent bond. And we make our polyatomic ion NH4 plus 1. We also have made a hydroxide polyatomic ion. People who draw better than me. Here's the example between your normal covalent bonds. So we have 2 hydrogens sharing their electrons. So lone electron, lone electron. Here's your shared pair of electrons, covalent bond. In your coordinate covalent bond, here's our hydrogen plus 1 ion. Here is your unshared pair of electrons right here that he bonds onto. I would, of course, color one of these in different so that you can see that's not a regular covalent bond. That is your coordinate covalent bond, sharing with an unshared pair of electrons. We also have a special case where atoms share more than 1 pair of electrons, and we have things that we call double or triple bonds. So oxygen forms an oxygen molecule with a double bond. That's as a structural model. As a Lewis dot model, that means his 2 lone electrons are going to match up with another oxygen's 2 lone electrons. Nitrogen makes a triple bond. We've learned that in the periodic table unit. People who draw better than me, let's look at their multiple bonds. Here's oxygen. So you have their unshared pairs and your 2 lone electrons, your unshared pairs, and your 2 lone electrons matching up. So here's your double bond. So we have 2 covalent bonds. We have compounds with carbon that will also make double bonds, where 2 of their orbitals will overlap, sharing their electrons. So there's a single bond between the hydrogens and the carbons, but a double bond in between the 2 carbons. If we draw that with sticks in a structural model, it would look like this. With the structural models, it's much easier to pick out where the double and triple bonds are because there's more than one line. When we talk about ionic and covalent bonds, there's a range, and how ionic or covalent a bond is based on the difference in the electronegativities. So they will talk about the ionic character or the covalent character, and it's not a set cut-off point. It's more like a rainbow, and it gradually changes from one to the other. So there will be some things when we look at them There'll be a covalent bond like hydrogen to chlorine, but when we put them to water, hydrogen and chlorine will act more like an ionic bond and it will actually dissociate. And those are some special cases, and it's generally with acids, things made with hydrogen. Just know that there's a range and there's not a definite cutoff point. Properties of molecular substances. If they call it a molecule, it is made with covalent bonds. If they're calling it a molecular substance, it's made with covalent bonds. Water is a molecular substance. Water is a molecular solid when it's ice. They are discrete particles. They are neutral. They share their electrons, so they look like noble gases. So if we look at some diagrams of when they share so that hydrogen can pretend he's helium. So when this side has the electrons, he looks like helium. And when this side has the electrons, he thinks he looks like helium. Neither of them are really helium, they're just sharing their electrons. The same happens with bigger compounds. So if we're looking at carbon dioxide, they're sharing. The oxygen gets to pretend he has 8 valence electrons. The carbons get to pretend they have 8. This makes them very stable, so they have lower, or they don't dissociate very well. They don't conduct electricity. Whether they are aqueous or solid, they're not going to conduct at all because they don't dissociate when you dump them in water. They can be solids or liquids or gases, and that's going to depend on these things we call intermolecular forces, which will depend on the shape of the molecule and the size of the molecule, how big or heavy it is. They tend to have low melting points. Sugar is a good example of a molecular solid. You can melt sugar on the stove, but you can't melt salt. Salt is ionic, high melting point. Sugar you can melt and make caramel, so low melting point. They never conduct electricity. Pure water does not conduct electricity. Covalent bonds can sometimes be so tight that we call them network bonds, network solids. The covalent bonds form crystals. They pull them in very tight, they form crystals, and you get open spaces and it changes their properties. They're very, very hard. They don't conduct ever, and one of the things that makes them different from other covalent substances is they have very high melting points. So normal covalent substances, soft, low melting points. Network solids are very hard with very high melting points. Diamond and quartz are your two big examples. Diamond and quartz. Silicon carbide would also be a network solid, but diamond and quartz are the two big ones. Last but not least, we have our metallic bonds. Positive ions in a sea of mobile electrons. Remembering that metals have very low ionization energies. That means they lose their electrons very easily. And those electrons all flow around, and they all share their electrons within the same sample. So the electrons float around the nuclei. Overall, it's neutral. They arrange themselves so there is generally the same distance between the atoms because they can only pack together so tight because they're round. But we have positive ions in this sea of mobile electrons. The electrons are constantly moving. Remember that it is those mobile electrons that give metals all of their properties. So positive ions in the sea of mobile electrons. Here's another diagram. A lot of times they like to add arrows to show you that the electrons are moving around. It lets them be malleable. It lets them have luster. It lets them be ductile. It lets them conduct very well. The mobile electrons are what are allowing the metals to conduct electricity so well. We have areas of charge. So the electrons in the positive nuclei push and pull the electrons through. They also help to push and pull heat through these moving electrons. Next lecture will be about intermolecular forces.